So let us see what happens if we consider the improper integral of non-negative functions. So the first thing one has to consider is the following, that if a function is non-negative, so here is the picture, then this is a, and then we want to integrate it up to plus infinity, then the integral function is monotonically increasing because, for instance, the area here up to C1 is less than the area up to C2. So f of C1, capital F of C1, is less than capital S of C2 if C1, provided that C1 is less than C2, so here less or equal, then capital F is monotonically increasing so it has limit for C going to plus infinity. And so the limit, of course, can be finite. In this case, we have a convergent improper integral, so the character is convergent, and so it is integrable in the improper sense, or can be divergent, the limit, so the improper integral is divergent and it is equal to plus infinity, but it cannot oscillate, it cannot be indeterminate. So this is the content of the first proposition. You consider a function f from the interval a plus infinity up to r, and f of x not negative, non-negative for every x larger than a. Moreover, we want f to be integrable in AC for every c larger than a. Notice that this condition is automatically satisfied if f is continuous. Then the improper integral of f from a to plus infinity is either convergent or divergent. Namely, with the definition that we gave, namely, f is integrable in the improper sense in the interval a plus infinity or diverges, the proper integral diverges but the improper integral of f in the interval a plus infinity cannot be indeterminate. Okay, so here, for the proof, we consider the points C1 and C2 in the following way. C1 is between A and C2, so capital F of C2 is equal, here the picture is here, is equal to the integral from A to C2 of F. So this is equal to the integral from A to C1 of F plus the integral from C1 to C2 again of the function f. Okay, so the integral on the whole interval is the sum of the integral from here up to here. So the difference is the integral here, this integral here. So this is equal to a capital F of C1 plus integral from C1 to C2. But since this integral here is non-negative, so we know that the function is non-negative, so the whole integral is non-negative, then this is larger than or equal to f of C1. Okay, so this means that f, capital F, is monotonically increasing. And then the limit for c going to plus infinity of f of c exists. And then the improper integral of f cannot be indeterminate. Okay, so this is just the translation in more mathematical symbols of what we said before, what we said here. So let us go to the first results that helps us to determine whether an improper integral is convergent or divergent, and this is called the comparison principle or criterion. I recall you that we are talking about non-negative functions, and so we have two functions, f and g, from the unbounded interval a plus infinity up to r. Both of them are integrable on AC, or every c larger than a. And moreover, f is not larger than g, and both are non-negative again. Then, again for every x larger than a. Then, there are two consequences if the improper integral of f diverges, then the improper integral of g diverges too. This is quite obvious. Okay, I'm saying that if the smaller quantity, the smaller improper integral is plus infinity, then the larger improper integral must be plus infinity too. Second, if on the other hand, the larger improper integral, so to say, the improper integral of g, is convergent, then the improper integral of f is convergent too. The proof is quite immediate. So since f is not larger than g, then the integral between a and c of f is not larger than the integral between a and c of g. That implies that the limit for c going to plus infinity preserves the same order by permanence of sign. Then, if the first proper integral is infinity, this infinity must be less than this quantity, but this quantity cannot be larger than infinity. So the integral of g is plus infinity. Vice versa. If this quantity, the proper integral of g, the larger one, is finite, then the improper integral of f is finite too. Okay, and this is the end. So this is a powerful criterion because once we know for a class of functions its behavior, we can use this class of function to compare with other functions. And in order to use this principle, we need to know the feature and the characteristic of at least a class of functions, so we need to have some prototypes. And so prototypes must be simple in order to get a conclusion about their convergence or divergence in a easy way. And so the simplest prototype are given by the powers. So the prototypes are function of the type f of x equal to 1 over x to the power alpha, with alpha larger than 0. X, for instance, from 1 to plus infinity, or from a. And so let us compute capital F of c, which is the integral between 1 and c of 1 over x to the alpha. So let us integrate, and we know that we have to distinguish two cases. The first case is alpha different from 1, and in this case we have x to the power minus alpha plus 1 divided by minus alpha plus 1 to be evaluated between 1 and c, and in the case alpha equal to 1, it is logarithm of x. Here we don't need to use the absolute value because x is larger than 1, so it's larger than 0 too, so it's positive between 1 and c. So and this is equal to c to the power minus alpha plus 1 minus 1 divided by 1 minus alpha for alpha different from 1, and here log c for alpha equal to 1. The second one is a computation that we already made in the example at the beginning, and then we also computed this quantity for alpha equal to 2. Okay, so now we have to take the limit for c going to plus infinity of f of c, which means here the limit for c going to plus infinity of c to the power minus alpha plus 1 minus 1 divided 1 minus alpha in the first case, and the limit for c going to plus infinity of the logarithm of c for alpha equal to 1. Now in the first case splits in two, because you see when you perform the first limit here, the limit of this quantity depends on whether the exponent here is positive or negative, so whether alpha is larger or smaller than 1. Then this is equal to the limit for c going to plus infinity of c for instance, let me write it clearly, minus 1 minus alpha minus 1 divided 1 minus alpha for alpha less than 1, and this is equal to plus infinity for alpha less than 1. Vice versa, the same limit for c going to plus infinity to c to the power minus alpha minus 1, just a different way to read it. And here what you have is that this quantity is positive, c goes to plus infinity, but there is a minus here, so here we have that c to the power minus alpha minus 1 goes to 0, and of course, sorry, here there was a minus here in front because I reverted the sign here. So we end up with 1 over alpha minus 1, which is not an infinite number, it is a true real number, this for alpha larger than 1, and of course limit for c going to plus infinity of log c, which is plus infinity for alpha equal to 1. So we have therefore the integral from 1 to plus infinity of 1 over x to the alpha thus converges for alpha larger than 1 and diverges for alpha less or equal 1. Of course, when alpha is negative, it diverges a fortiori. I don't want to say anything about that, but here let me give you a picture, for instance, here for alpha equal to 1, and here we already have divergence, and then this other graph is for alpha larger than 1, and for alpha smaller than 1, we are, for instance, here. So, above the hyperbola for alpha equal to 1, we have that the improper integral of our prototype diverges, and here it converges. On the hyperbola, it diverges. Okay? So, armed with this prototype, you can already discuss some example. For instance, in this example here, so the example is determine the behavior of the improper integral and this is the integral between 1 and plus infinity of cosine of x divided by x to the power 3/2 dx. This, of course, is non-negative. And then notice that cosine of x is less than 1. So cosine of x over x to the power 3/2 is less than 1 over x to the power 3/2. And this is a prototype, one of our prototypes, with alpha equal to 3 over 2, which is larger than 1. So we have that this improper integral converges. So this improper integral from 1 to plus infinity converges. Then, by the comparison criterion, we have that the improper integral given at the beginning, so cosine of x divided by x over x to the 3/2 is convergent. Okay, and this is the only criterion that we give for at least for now for this improper integrals. And now we go improper integrals with non-negative terms, non-negative functions, and then we go to improper integrals of functions with either signs. But first, before going there, I want to give you a remark that says in the prototypes, the first extreme of integration may also not be 1. For every a larger than 0, the integral from a to plus infinity of dx over x to the alpha converges if alpha is larger than 1 and diverges if not alpha less or equal to 1. Okay, so let us stop here.